This is a photomultiplier. It counts individual photons. This is one easy way that we know photons are particles. If light wasn't made up of particles, we couldn't count them. Every instrument that has ever been designed to detect weak light has shown the same thing. Light is made up of particles. Today we are going to examine how light interacts with matter. And all you need to know about light to follow along are the familiar everyday properties of light. Like light goes in a straight line. It bends when it goes into water. When it reflects off a mirror, the angle at which it hits the mirror is equal to the angle at which it leaves the mirror. Light can be separated into colors. You can see beautiful colors on a puddle if there's a little bit of oil on it. A lens focuses light, and so on. Almost everyone has experienced looking out a window and seeing themselves partly reflected in the glass. Let me tell you about an experiment in which photons of just one color, say red, are emitted from a light source down towards a block of glass. A photomultiplier is placed at point A above the glass to catch any photons that are reflected from the front surface. And another photomultiplier is placed at point B inside the glass. And we find that on average, every 100 photons that we shine straight down on the glass, only 4 arrive back at A, while 96 arrive at B. But now we have a real problem. If we think about each photon encountering the glass, we might wonder, how does the photon decide whether to go through the glass or reflect back into the room? Okay, let's do it again. Only this time, we replace the block of glass with a thin sheet of glass, and we move photomultiplier B to the other side. Now the photons can reflect off either the front or the back surface of the glass in order to show up at A. We might expect that 4% would reflect off the front surface and 4% of the remaining photons to reflect off the back, making a total of about 8%. But what we find is that with some sheets of glass, 15 or 16 photons find their way back to A, and with other sheets of glass, we get only 1 or 2. Some sheets of glass reflect 10%, and others eliminate particle reflections altogether. After checking the glass sheets very carefully, we find they differ in only one respect. They vary ever so slightly in thickness. With this as a clue, we redo the experiment with progressively thicker and thicker glass. And sure enough, we see the particle reflection vary from 0 to 16%, and back to 0, and back to 16%, and back to 0 in a continuous cycle. Wow! How can that happen? How can adding a second surface somehow turn off the reflection from the front surface? How does the photon know how many surfaces it will encounter before it gets to them? The answer is that each photon travels every possible path simultaneously. There's no decision-making at all. And the probability of each final outcome is determined by adding the probability from each possible path. And each individual path probability can be represented by a little arrow, such that the actual probability is the square of the length of the arrow. For example, in the first experiment, we found that the probability that the photon would arrive at photomultiplier A was 4%. That corresponds to an arrow whose length is 0.2, because 0.2 squared is 0.04. In the second experiment, there are 2 paths for the photon to get to A. So there must be 2 arrows, and we must add them. But how do we add arrows? We simply put the tail of the second arrow at the head of the first and draw a new arrow from the tail of the first to the head of the second. Now, to determine the direction that each arrow points, imagine that there is a stopwatch that times the movement of the photons along a path. When the photon leaves the source, we can start the stopwatch. And when the photon triggers the photomultiplier, we can stop the stopwatch. And whatever direction the hand points is the direction of the arrow for that path. Except we need one more rule. When the path includes reflection off the front surface of the glass, we reverse the direction of the arrow. Let's draw the arrows from the case of light reflecting from a very thin plate of glass. For the front reflection arrow, we start the stopwatch when the photon leaves the emitter. It bounces off the front surface and enters the photomultiplier, and we stop the stopwatch. Then we draw a little arrow of length 0.2 in the direction opposite that of the stopwatch hand. For the back surface reflection arrow, we repeat the procedure. And when the photon arrives at the photomultiplier, we see that the stopwatch hand is pointed in almost the same direction as for the other path. Because the glass is so thin, the back reflection path is about the same length as the first, and the stopwatch hand has turned only a tiny bit more. So we draw a little arrow of length 0.2 in the same direction that the stopwatch is pointing. Now let's combine the arrows. Since they are nearly the same length but point in the opposite directions, the final arrow has a length of nearly 0, and its square is even closer to 0. So the probability of light being reflected from a really thin layer of glass is essentially 0. As we replace the glass with increasingly thicker pieces, we can see that the stopwatch for the second path would turn more and more as the path gets longer. So the resultant arrow gets longer and longer as well, and the probability of reflection grows. When the glass is just thick enough for the stopwatch to make a half turn, the length of the two arrows add to give us 0.4. And the probability of reflection is the square of this, or 16%. As the glass keeps getting thicker until the stopwatch has made a complete extra turn, the resultant arrow is back to 0, and the probability of reflection is back to 0, and the cycle starts again. If we repeat this experiment with other colors of light, we would get similar results. Depending on the thickness of the layer of glass, we would get repeating cycles of reflection probabilities ranging from 0% to 16% and back to 0. But with one difference. The stopwatch hand turns at different speeds for each different color of light. So the thickness of the glass that results in 0% or 16% reflection is different for each color. And that explains the colors we see when the light is reflected from a thin film of oil on a mud puddle. The oil film is never exactly uniform in thickness, so different sections of the film are just the right thickness for reflecting red light, or blue or green light. So we see the entire rainbow of colors reflected from different areas of the film. Now let's replace the glass with a mirror. We move the light source off to one side and move the photomultiplier off to the other side. And let's add a screen in the middle so the photons can't go straight from the source to the photomultiplier. But we have to reflect off the mirror. Now our experience suggests to us that the photons will bounce off the center of the mirror because that's where the angle of incidence is equal to the angle of reflection. And our intuition makes it seem obvious that the parts of the mirror out to the ends don't have much to do with it. But that would take us back to the concept of smart light. How does the light know that it's supposed to travel in a single path? So let's examine how our idea that light travels every path can give us the right answer. Start with the fact that light has equal probability of reflecting off the mirror at every point. So when we draw our arrows, they will all have the same length. And let's simplify the situation by first looking at the 15 representative paths. These paths. Now, as we said before, the length of the arrow for every path is the same length, but we still need to calculate the direction for each arrow. And remember that the direction is determined by how much the stopwatch has turned during the photon's trip. The paths out near the ends of the mirror are the longest. Not only that, the change in length from path to path is greatest out near the ends as well. So the adjacent arrows will turn a lot from path to path. The first four will look something like this. As we get closer to the middle, the paths get shorter, and the difference in path length from path to path is much smaller. So the arrow turns a lot less for adjacent paths. The next 7 arrows look something like this. And the arrows for the paths at the right end are just like the arrows for the similar paths at the left end. Now let's join the arrows head to tail and draw the final arrow. And what do we see? First, the ends of the mirror are not important, because the times are different from path to path. The arrows from the first part just go in a spiral. If we chopped off the ends of the mirror, it wouldn't change the end result very much. And the paths near the center contribute most to the final arrow. This is where the time of travel is the least. This is where the angle of incident equals the angle of reflection. And that is why you can get away with saying that light only reflects off the single point in the middle, even though that it's wrong. Let's test the idea that reflection is really happening all over the mirror. Let's remove the parts of the mirror in the middle and on the right, leaving only this portion on the left. And now let's force the arrows on the left to point in pretty much the same direction instead of pointing all over the place. We do this by noting how fast the stopwatch is turning, and by scraping away all the portions of the mirror that would give arrows that point to the left. Now when we add our arrows, we get a final arrow of substantial length. So we should get a strong reflection from our off to the side scraped up mirror. Does this really happen? Yes, it does. This type of mirror is called a diffraction grating, and it works like a charm. And since the stopwatch spins at different rates for different colors, the spacing in diffraction grating changes from different colors of light. But instead of actually changing the spacing, we can just move the photomultiplier up and down a bit. Changing the angle achieves the same end as changing the spacing. This is why a series of grooves, like on a music CD, reflect different colors of light at different angles. So a grating shows that light really reflects from all parts of the mirror, and light isn't so smart after all. We could continue describing interference and other phenomena with our every path method and spinning arrows, but suffice to say, the method works. Always works. Exactly works. So let's turn our attention to the interaction of light and electrons. We can apply the every path method here as well. We start by drawing diagrams of every possible path for an interaction to occur. And surprisingly, we can reduce the task of making these diagrams to just 3 fundamental actions that we need consider. Every possible interaction diagram can be reduced to combinations of these 3. 1. A photon goes from place to place. 2. An electron goes from place to place. 3. An electron emits or absorbs a photon. Each of these basic actions has an amplitude, an arrow, that can be calculated according to certain rules. Let's draw a diagram of one action. A photon goes from place to place. We put time on the vertical axis and space on the horizontal axis, and we will represent the photon by a wiggly line. So basic action 1 looks like this. There is a certain probability amplitude for the photon to go from A to B. Let's call it P, A to B. And there is a formula for the size of the corresponding arrow. In the second basic action, an electron goes from point A to point B. Let's call the amplitude for this action E, A to B. Notice electrons are represented as straight lines. The formula for the amplitude of this action includes a very special number called n. And it's interesting to note that the formula for P, A to B, a photon going from point A to point B, is the same as E, A to B, an electron going from point A to point B, if n is set to 0. The third basic action is an electron emits or absorbs a photon. This action is called a coupling. Every coupling is a junction between 2 straight lines and a wavy line. There's no complicated formula for the amplitude of coupling. It is just a number, and we call it J. Its value is about negative 0.1. Now let's calculate the probability that 2 electrons at 2 points, 1 and 2, end up at points 3 and 4. This event could happen in 2 ways. The electron at point 1 could go to 3, given an amplitude of E 1 to 3. And the electron at 2 goes to 4, giving E 2 to 4. So the overall amplitude for this path is E 1 to 3 times E 2 to 4. Another way would have electron 1 go to 4 and electron 2 go to 3. This would have an amplitude of E 1 to 4 times E 2 to 3. And of course, the final step is to add these 2 arrows to get the total amplitude. This would be a good first approximation, but we should also consider other ways this event could happen. For each of the ways we just described, one electron could emit a photon on the way, and the other electron could absorb a photon along the way. Calculating this complicated amplitude involves the number J we mentioned earlier. It is shown here. And there are more possibilities. This looks hopeless, but the number J will come to our rescue. The first ways this event could happen have no J's in the calculation. The next way had J times J. And the last would have J times J times J times J. And since J times J is less than 0.01, the arrow from this possibility is only 1% as long as the arrow for the first way. And the J times J times J times J path is less than 1/10,000th as long as the no J method. So you only have to go to the more complicated possibilities if you need increased accuracy. When an electron is placed in an external magnetic field, it exhibits a response called its magnetic moment. The diagram for the first approximation of the magnetic moment of an electron is very simple. An electron goes from place to place and couples with a photon from a magnet. This gives a value of 1 for the magnetic moment. After some years, it was discovered that the value was not exactly 1, but something like 1.00116. In 1948, the first second-order corrections were made. They involved J times J terms from diagrams like this. To calculate the contributions from this class of diagrams, we had to make an arrow for every place in space-time that the photon could be emitted and every place that it could be absorbed. And since then, experiments have measured the magnetic moment to even greater accuracy. So now we needed to consider all the ways the electron can go from place to place with 4 extra couplings. It took 2 groups of physicists 2 years to calculate these terms. The term with 6 extra J's involves even more possible ways the event could happen. It took 20 more years to get this extra accuracy figured into the theoretical value of the magnetic moment. With better computers, more and more J's have been added. And theory and experiment now agree in more than 16 decimal places. If this accuracy was matched in measuring the distance from the Earth to the Moon, we would know the lunar distance to an accuracy smaller than the thickness of a single human hair. Quantum electrodynamics is perhaps the single most successful physical theory ever devised. It forms the bedrock foundations for all of today's unification theories, like the Standard Model. QED, Quod erat demonstrandum.